All right, today we're going to talk about the limit comparison test. This one is super handy because at this point, we know enough about series that converge and series that diverge. And so, what the limit comparison test let us do is it lets us take a series that looks like a series that either converges or diverges that we know well, and we can compare it to that series to determine what happens. So as long as A sub n is positive and B sub n is positive, like we're saying that the nth term is greater than 0 for these two different series, then if the limit as n approaches infinity of A sub n over B sub n, now I will tell you, typically A sub n is going to be the given series and B sub n is going to be the chosen series. So you're going to make that choice of what series you want to compare it to. If that limit as n approaches infinity equals L, meaning L is some finite and positive value, then what that tells us is that A sub n and B sub n both behave the same way. So either they both converge or they both diverge. So there's a lot of power in this test with choosing the test you're going to converge or compare it to. If I compare my series with a divergent series and I get that the limit is equal to like 2, then I know that my series also diverges because whatever the one I choose does is going to be the same as what the one that I'm given does, and vice versa. Okay. Most series on the AP exam are going to be transformations of a parent series. And that is what's really important. So our goal here is to recognize which parent series, P series, geometric series, etc. And this is where the harmonic becomes really important, which parent series it belongs to. And we get to choose. We want to compare it to its parent series. So for example, A, we want to determine whether the series converges or diverges. We want the sum from 1 to infinity of 1 over 3n squared minus 4n plus 5. Well, I see right away that this is a polynomial with a power of 2. So I'm going to choose to compare this to the series 1 over n squared. That's a p series where n is greater than 1. So whoops, we know that let me erase that mess. We know that this converges. Okay. So that's going to be our b sub n. So what we want to look at is we want to look at the limit as n approaches infinity of our original series, 1 over 3n squared minus 4n plus 5, divided by the series that we're comparing to, which is 1 over n squared. That gives us the limit as n approaches infinity of, we keep change flip, that's going to give us n squared over 3n squared minus 4n plus 5. This is where our limits at infinity are really important because this comes out to 1/3. That is finite and it is positive. So that means that our two series behave the same. So since 1 over n squared converges, that means that the sum from n equals 1 to infinity of 1 over 3n squared minus 4n plus 5 converges. And now we have to be specific by limit comparison with the convergent P series, the sum from n equals 1 to infinity of 1 over n squared. That would be our answer. That's what we are looking for. We compared it to a series that converges and we got a limit that exists. It is positive and it is a finite value. Therefore, the series converges. Okay, let's look at B. We want the sum from 1 to infinity of 1 over the square root of 3n minus 2. Again, for this one, we need to think about what we want to compare this to. I would compare this also with a P series. I would compare this to 1 over the square root of n, which is 1 over n to the 1/2, okay? This, oops, I'm sorry, I'm throwing this everywhere. This is a divergent P series. So again, if we get a limit that exists and is positive, then we know that our series also diverges. So take a moment, put the video on pause, see if you can find that limit, the limit of what we have divided by what we're comparing it to. Pause and see what you get there. Okay, so for this one, when we compare, we end up with the square root of n over the square root of 3n minus 2. When you take that limit at infinity, both of the n's are to the 1/2 power. So we just get the ratio of their coefficients, which is 1 over, in this case, the square root of 3, because the 3 is inside the square root. We got a limit that is finite and positive. Therefore, this series diverges because we compared it to a divergent P series, 1 over n to the 1/2. And again, that diverges because P is between 0 and 1/2. So let's look at, let's look at two more. Example C. We need to decide what we want to compare this to. Now, this one is not as straightforward. I would, in this case, because we have n squared over 4n to the 5th, if we simplify that down, I would actually compare this one to 1 over n cubed, because n squared over n to the 5th simplifies to n cubed. Now, you can compare it to anything, but that would be the simplest thing to compare it to. So that's what I would suggest. Go ahead and pause your video and see if you can decide whether this converges or diverges. All right, you should get that this one also converges. We chose to compare it to a convergent P series. Okay, now when we take that limit, we have to do a little bit of algebra here. We end up with n cubed times n squared minus 10 over 4n to the 5th plus n cubed. We need to simplify that. Well, we can factor in n cubed out of the denominator, and then we have the same power in the numerator and the denominator, so this becomes 1/4 when we take our limit. So since we got a positive real number value for our limit, that means that it also converges because we compared it to a convergent P series. Now for D is a little bit trickier. Okay. For D, I look at this and I'm not 100% sure what to compare it to. Maybe 1 over n squared, because the n over n cubed will reduce to 1 squared. But the first thing that I notice is that I have an exponential in the top, which is far more powerful than any polynomial. So in this case, I actually want to try looking at the nth term. The limit as n approaches infinity of just what we have here, n times 2 to the n over 4n cubed plus 1, that does not equal 0. And that is all that matters. That's going to go to infinity. So we can say that this one right away diverges by nth term test. Okay, so that one you don't need to use limit comparison at all. If you do use limit comparison, you're going to get infinity for your limit, which means, now this is just like with all the other theorems. This says if the limit is finite and positive, then the series behave the same way. If it is not finite and positive, then we just don't know. And that means this test is no good and we have to try something else. So that's what would happen in this case. If you tried to use limit comparison, it would fail and you would have to try something else. Okay. I'm going to ask you to go ahead and pause and try on your own this last example and see what you think. See if you can decide what you would compare it to. Think about this in terms of exponents and see what you come up with. I'll come back in a second. If you're not sure where to start, I would suggest comparing this to 1 over n to the 3 halves. Right now, we have essentially n to the 1 half over n squared. If you simplify that down, we get 1 over n to the 3 halves. So if you weren't sure what to compare that with, try that. So when we do this, we end up with the limit coming out equal to 1. Again, that is a value that is finite and positive. So since 3 halves is greater than 1, 1 over n to the 3 halves, that series is going to converge. So that means that our series also converges by limit comparison to the sum of 1 over n to the 3 halves. So that's the idea of limit comparison. Don't forget on examples like D, you can always fall back on the nth term test for divergence, especially that's really helpful if you recognize right away that the top is more powerful than the bottom. Otherwise, pick a convenient series that you can compare it to, choose something that we know something about, and that is where we will go from.